Hello. In the last class, we discussed half wave uncontrolled rectification. What are our observations? There was one diode in between the source and the load. We found that as the load inductance increases, the duration for which diode conduct is also increases. But then voltage applied to the load becomes negative. Therefore, the rate at which the current decays also increases. Instead, if we connect a diode across the load beyond pi, this diode connected across the load, which is also known as a freewheeling diode, starts conducting. Now the voltage applied to the load becomes 0, current decays slowly. Okay. What was the third point that we discussed? When the diode is on, the load voltage is the same as the source voltage. It is independent of type of load. You can have a RL or RLE, whatever may be the type of load, so load voltage is same as the source voltage. And when the diode is off, the load voltage depends on the type of load. If it is a passive load, voltage is 0, and if it is an active load, in the sense if there is a battery RLE type of load, voltage applied to the load is now E. The fourth important point that we found was, if the current is discontinuous and if there is a RLE type of load, diode starts conducting when the instantaneous value of the input voltage is equal to E. In other words, alpha is sine inverse E divided by Vm. And if the load current is continuous, diode starts conducting at the positive 0 crossing. I will repeat, if the current is continuous, diode starts conducting at the positive 0 crossing. It is independent of type of load. Even if you have a E there, it does not matter. It is because of L di by dt. Voltage across the inductor changes, and that voltage forward biases the diode. So in half wave rectification, applied voltage to the load is either 0 or negative beyond pi. Other than whatever 2 points that we discussed, there is a reduction in the output voltage, also the increase in the current decay, the ripple in the output voltage increases. So instead, we will see what happens in the full wave rectification. A very popular power circuit which is used in power supplies, using a center top transformer with primary number of turns is N1, N2, and here N2. Two diodes, cathodes are tied together, and load is connected between the ground, between the common point and the ground. This point and this point is the same. When the instantaneous when this point is positive, even this is also positive, this also will be positive. So in the positive half, D1 conducts, and in the negative half, D2 conducts. So what is the equivalent circuit when D1 conducts? V11 is the voltage induced in the upper half of the transformer. In the V12 is the voltage induced in the lower half of the secondary of the transformer. when the D1 conducts, since the cathodes are tied together, this point gets connected to the cathode of D2. So, what is the voltage that is appearing across D2? Of course, KVL has to hold good. It is minus of V11 plus V12. So, what is the maximum voltage that is appearing across the load? It is minus 2 V11 max, where V11 is N2 by N1 into V in, or the peak, twice the peak of the secondary voltage that is appearing across the load. Diode should be able to withstand twice the Vm, Average output voltage is given by 2 Vm by pi. Remember, in half wave rectification it is Vm by pi. Now there is an increase in the voltage, 2 Vm by pi. I am not going to discuss about the RMS value, ripple value. I have told you the procedure how to find out. You follow the same procedure. Let me repeat. I will use minimum number of differential equations. Most of the time I will use a graphical approach. Writing a differential equation, solving, I think anyone can do it. Now consider a common cathode configuration. What do you mean a common cathode configuration? I have a large number of diodes whose cathodes are connected together, and there is a load here, and I have given a various potentials to the anodes. Now which one of them will conduct? There is a plus 5 volts, plus 10, minus 5. We know that we cannot have a situation wherein a positive voltage appearing across the load, appearing across the diode. The moment the voltage across it is 0.7, it conducts. Assume that D1 conducts. If D1 conducts, cathode potential becomes 4.3, and if I consider it is to be ideal, it becomes 5. Then what happens to D2? Anode potential is 10 volts, cathode is 5. So voltage across the diode is 5 volts. You can't have that situation. So therefore, D1 cannot conduct, only D2 can conduct, because if D2 conducts, cathode potential becomes 9.3 or so, or 10 itself. D1 gets reverse bias, cathode is 10, anode is 5. Similarly, D3, cathode is 10, anode is minus 5. So what is the conclusion here? In a common cathode configuration, diode whose anode potential is maximum will conduct. Okay, I will repeat. In a common cathode configuration, diode whose anode potential is maximum will conduct. What happens in common anode configuration? I have again a large number of diodes, anodes are tied together, and cathode there are various potentials. I am not going to talk about where this point is connected, let us not worry. Now what happens, which diode conducts here? Let us assume that D1 conducts. If D1 conducts, potential of X is 5 volts or maybe 5.7. Okay. If potential of X is 5.7, cathode potential of D2 is 10. In that case, D2 is reverse bias, D2 cannot conduct. But then what happens to D3? Anode potential is 5.7, cathode potential is 5. The potential difference across it is approximately 10.7 volts. You can't have that situation. So therefore, D1 cannot conduct. Let us see what happens if D3 conducts. If D3 conducts, voltage potential of X is either minus 5 or minus 4.3 if I assume a 0.7 volts across the diode. If potential of X is 4.3, D2 is reverse bias, minus 4.3 minus 10, D1 is also, D2 is reverse biased, even D1 is also reverse biased, minus 4.3 plus 5. So therefore, in common anode configuration, diode whose cathode potential is minimum will conduct. So I will repeat, diode whose cathode potential is minimum will conduct in common anode configuration. So you need to remember these 2 points. We will go to the next. Single phase bridge, very popular. There are 2 diodes, D1 and D3 form a common cathode configuration, D4 and D2 form a common anode configuration. In the positive of, potential of A is higher than potential of B, so therefore D1 starts conducting, and in the lower half D2 starts conducting. So voltage apply when D1 and D2 starts conducting, voltage applied to the load is same as the input voltage. Here is the equivalent circuit: source D1, load D2, back to source. Vi is equal to V0. The circuit equation is Vm sin omega t is equal to R into I plus L di by dt. Solution we have already discussed. I reaches a peak value in between pi by 2 and pi. At that instant, instantaneous value of the input voltage is R into I max, because L di by dt when I is equal to I max is 0. At omega t is equal to pi plus, potential of B becomes higher than potential of A. So what happens? D3 starts conducting. The moment D3 starts conducting, cathode potential of D3 is same as the potential of B, assuming a diode to be ideal. In that situation, a negative voltage appears across D1, because potential of A is less than potential of B in the negative half, and cathode potential of D1 is the potential of B. So therefore a negative voltage appears across D1, diode turns off. Same thing happens in the lower half also. So therefore in the negative half, D3, load, D4, back to source. This is the equivalent circuit. In the positive half, current at reaches maximum somewhere in between pi by 2 to pi. It starts decreasing. Depending upon the load parameters, it continues to decrease, and again it starts increasing in the negative half cycle. And the instant when the current starts increasing, at that instant the KVL is Vi is equal to I min into R. I will repeat, at this instant Vi should be equal to I min into R, whereas here it is Vi is equal to I max into R. In both these points, L di by dt is 0. So therefore, current continues to decrease till Vi is equal to R into I min. Beyond that point, current again starts increasing, and after some time a steady state is reached, and depending upon the load parameters, if the load is highly inductive, current increases, decreases and attains a steady value. So at steady state, if the load is highly inductive, I can assume that load current becomes almost constant. When the diodes are on, the source current is same as the load current. Input voltage may be a sinusoid. Since the load is highly inductive, we assume that IL becomes almost constant. Therefore, source current will not be a sinusoid. If I assume that source current is constant and ripple free, if I assume the load current to be constant and ripple free, the source current is a square waveform, is a constant till 0 to pi or n pi to n plus 1 pi, and it is minus I naught from n plus 1 pi to n plus 2 pi. This I naught is the magnitude of the load current, constant I naught. Source is a sinusoid, input voltage is a sinusoid, whereas the current is a rectangular waveform. So what are the various parameters that have to be defined now? It is an odd function. So if I write the Fourier series, we will have all odd components. What is the peak of the fundamental? It is given by 4 I naught by pi. It is the magnitude of the fundamental, or the magnitude of the first component. In other sense, 4 I naught by pi into sine omega t, that is the magnitude. It has a third harmonic component, fifth, seventh, I mean all odd harmonics are present. Now what is the displacement angle? It is the angle between the fundamental component of the input voltage and the fundamental component of the source current. It is the fundamental component of the input voltage and the fundamental component of the source current. If I plot the fundamental component of the source current, it looks like this, whose frequency is the same as the input voltage. You will find that these two, voltage and the fundamental component of the source current, are in phase. In other words, displacement angle is 0. Displacement angle is 0. What is the displacement factor? It is the cos of the displacement angle. In other words, it is 1, unity. What is the input power factor? It is defined as mean input power divided by RMS input VA. We know that it is only the fundamental component of the input voltage and the input current are responsible for power transfer. I will repeat, it is a fundamental component of the input voltage and the current are responsible for power transfer. the higher frequency components, the all other odd components will give rise to additional I square R heating. They do not contribute to power transfer, they contribute only to additional I square R losses. So, input power is given by V1 I1 cos of the angle between V1 and I1. Both V1 and I1 are RMS values of the fundamental component of the V1, and I1 is the RMS value of the fundamental component of the input current. Since we had assumed that voltage is a pure sinusoid, V1 is equal to Vrms itself. Source current is a square waveform. The third, fifth, seventh, all harmonics are there. We have assumed that load is highly inductive. The load current remains constant, whose magnitude is I naught. So, the RMS value of the source current is I naught itself. RMS value of the fundamental component is given by this equation, 4 I naught by square root of 2 by pi. So, therefore, if you substitute all these values in this equation, power factor becomes 0.9. It is lagging. Remember, almost all the power electronic circuits, power factor is lagging. So, this factor decides the volt ampere requirement. The size of the equipment that is required to feed a load depends on VA requirement and not on just on power. What is the total harmonic distortion? It is given by, we have defined already, it is the ripple divided by the fundamental component. This we have already defined, IRMS squared minus I1 squared, the square root divided by the fundamental component. It is as high as 49%. Let us see sometime later in the course how exactly to reduce this total harmonic distortion. The 49% is the ripple content. It gives rise to only additional I square R heating in the load. It also affects the source side. We will see sometime later the effects. What happens if the load is purely inductive? In the half wave rectification, when the load is purely inductive, diode conducted for the entire 2 pi radians, average voltage across the load becomes 0, current reaches peak at omega t is equal to pi and becomes minimum at omega t is equal to 2 pi. What happens in the full wave rectification? Current starts from 0, sorry, it is not linear, okay, it increases, reaches a peak at omega t is equal to pi, again at omega t is equal to pi plus a positive voltage is appearing across the load. If the positive voltage appearing across the load, it implies that di by dt has to be positive, because L di by dt is equal to V. So, left and right hand side is positive, so di by dt has to be positive. So, current again starts increasing, whereas in half wave rectification from pi to 2 pi, the voltage appearing across the load was negative, that is why di by dt becomes negative. Whereas in full wave rectification, it is positive voltage appearing across the load beyond pi, so currents again starts increasing. Please, it is not linear, again increase, so on. So, current goes on increasing till either a diode has to fail or the source has to fail or something has to fail. There is no steady state here, because L di by dt is always positive. If L di by dt is positive, di by dt is positive, current goes on increasing. no steady state. Okay. So far we discussed about uncontrolled rectification, full wave as well as half wave. Now we will go in for controlled rectification. I need to use a 3 element device. So we have already discussed about the SCR, anode, cathode and the gate. So we can turn on the SCR when it is forward biased by applying a positive gate signal with respect to the cathode, that we have already studied. Okay. So when the device is on, circuit behavior is same as that of the diode circuit. That is almost the same, there is no much difference. But there could be some difference in the waveforms, we will see. So in the positive half, I am assuming the load to be passive. Somewhere in between 0 to pi I am triggering, alpha is the trigger angle, finite Ig is flowing, SCR turns on. The moment that SCR turns on, SCR is triggered somewhere at this instant, input voltage is the same as the load voltage. So the instantaneous value of the input voltage is the same as the load voltage. So load voltage jumps to this value. It follows the input till the current becomes 0. If the load is purely resistive, current becomes 0 at omega t is equal to pi. SCR turns off till you trigger again in the positive half, SCR is off. So what is the voltage appearing across the SCR? It is triggered only at alpha. From omega t is equal to 0 to alpha, it is in the forward blocking mode. It is forward biased, a positive voltage is appearing, but then there is no gate signal, so it cannot conduct. So this is Vi. At omega t is equal to pi, it becomes 0. Input voltage is also becoming negative, voltage across it also become negative till 2 pi and cycle continues. This is for the purely resistive load. Average value we can determine by integrating this waveform. What happens if the load is a purely inductive? Again we have triggered the SCR at alpha. We know that average voltage across the inductor is 0 here, or should be 0. Purely inductive, circuit equation is, when that SCR is on, Vi is equal to L di by dt. Instantaneous value of the input voltage is 0 at omega t is equal to pi. Current starts increasing, reaches a peak and starts decreasing. So this area is positive L di by dt. I said average voltage across the inductor should be 0. So if it has started conducting at alpha, or if in the positive half the duration is pi minus alpha, so it has to be equal to, even in the negative half, pi minus alpha. So SCR turns off at 2 pi minus alpha, so that average voltage across the inductor becomes 0. Positive L di by dt, negative L di by dt. Current starts decreasing at pi, it becomes 0 at 2 pi minus alpha. So this is the difference between controlled rectification and uncontrolled rectification. Only thing you need to know is type of load and the circuit equation. You can solve that. off controlled bridge. Just now we studied uncontrolled bridge. Now let us discuss off controlled bridge, wherein there are two SCRs and two diodes. Okay, configuration 1. Okay. What are the other assumptions? Other assumptions are load is highly inductive, so load current is assumed to be constant and ripple free. The magnitude of IL is I naught. Whatever the analysis we did for diode circuit, they are valid. And source side inductance is 0. We will see why it is 0 and what happens if it is finite sometime later. As of now, we will assume that source side inductance is 0. Another thing is SCR turns off immediately when a negative voltage is applied to it. In the sense, though all the devices are non-ideal, they require a finite time to attain the forward blocking mode, the forward blocking capability. In the analysis, we will assume that all the devices are ideal, turn off as well as turn on time is 0. In other words, the moment you turn on, the moment you apply a positive gate signal to the thyristor, it turns on, and the moment you apply a negative voltage across it, it turns off. Okay. In the positive of course, T1 and D3, they form a common cathode configuration, and T4 and D2, they form a common anode configuration. In the positive of potential of A is higher than potential of B. So T1, if the gate signal is applied, T1 can conduct. Let us assume that in the positive of somewhere at omega t is equal to alpha, T1 is triggered. In the lower half, since T4 and D2 form a common anode configuration, device whose cathode potential is least will start conducting, so D2 starts conducting. So this is the equivalent circuit. Source T1, load D2. Sorry, back to the source. Here are the waveforms. At omega t is equal to alpha, T1 is triggered. At omega t is equal to pi plus alpha, T4 is triggered. So when T1 and D1 are conducting, load voltage is same as the source voltage. It becomes 0 at omega t is equal to pi. What happens from pi to pi plus alpha? T4 is triggered only at pi plus alpha. In the upper half, potential of B is higher than potential of A in the negative half. At omega t is equal to pi plus, potential of B becomes higher than potential of A. Immediately D3 starts conducting. The moment D3 starts conducting, a negative voltage appears across T1, T1 turns off. Nothing of that sort happens in the lower half, because though T4 is forward biased, we have not applied a gate signal to T4. So T4 is still in forward blocking mode. Load is highly inductive, so currents starts flowing through D2 and D3. In other words, current freewheels through D3 and D2. The equivalent circuit is D3 to D2. So, this is the condition. D2 was conducting, potential of A though it is higher than potential of B, we have an open circuit here, T4 is not triggered. So, D2 continues to conduct, here is the load circuit, voltage applied to the load is 0, source current is 0. Alpha current free wheels through D3 to D2. What happens at omega t is equal to pi? T4 was forward biased at omega t is equal to pi. So, at pi plus alpha it is triggered, it starts conducting. The moment it starts conducting, potential of A will become the anode potential of D2. In the negative half, potential of B is higher than potential of A. A negative voltage appears across D2. D2 turns off. So, the equivalent circuit is now source D3, load T4 and back. So, in the first half or from alpha to pi, current was flowing in this fashion, or if I show it in the bridge, it is T1 load D2. In the second half, source current has reversed, pi plus alpha to 2 pi, it is enters this back to 2. How do we turn off T1? T1 turns off the moment D3 starts conducting. When the potential of B becomes higher than potential of A, D3 starts conducting, a negative line voltage appears across T1, Hence, this sort of a turn off process is known as line commutation. Why it is line commutation? I am using the input line voltage itself to turn off the conducting thyristor. There are other processes that we will see sometime later, other process of turning off the thyristors we will see later. So, this is known as the line commutation. The input voltage itself is used to turn off the thyristor, hence the name, the line commutation. The source current waveform, pi to alpha to pi, it is I naught sorry, pi plus alpha to 2 pi, it is I naught in the negative direction. What happens again at omega t is equal to 2 pi? At omega t is equal to 2 pi plus, potential of B becomes less than potential of A, maybe, but then T1 is not triggered. T1 is triggered at only after alpha, 2 pi plus alpha. Till then we have an open circuit here, So, potential of A does not appear at the cathode of D3. So, D3 continues to conduct. I repeat, D3 continues to conduct, whereas in the lower half we have an uncontrolled device D2, a common anode configuration. So, immediately D2 starts conducting. The moment D2 starts conducting, a negative line voltage appears across T4, T4 turns off. So current again starts flowing in D3 and D2. So from 2 pi to 2 pi plus alpha, D3 and D2 continues to conduct. Voltage applied to the load is 0. Voltage applied to the load is 0. T4 is again commutated or turned off using the line voltage, hence the name line commutation. So if I plot the duration of diode conduction with time, you will find that D2 starts conducting if I plot D3 starts conducting at pi, continues to conduct till 2 pi plus alpha. Please, this should be ID3. I am sorry about that, it should be ID3. So D3 starts conducting at pi plus, it continues to conduct till 2 pi plus alpha. Please correct it. This is D2, this is D2, and this is D3. D2, D3, D2, D3. Sorry, 2 pi plus alpha. Whereas thyristor conducts from alpha to pi itself. Thyristor conducts from alpha to pi. So if you see in one circuit, some devices are conducting for a longer duration and some devices conduct for a very short duration. Magnitude of current that is flowing through each device is same. I have assumed load to be highly inductive. So it is load current is constant and ripple free, magnitude is I0. So average current rating of thyristors is less than the average current rating of the diodes, because they conduct for a shorter duration. Okay. Somehow that is not desirable. In one circuit, average current rating of some devices is different from that of the others. So please, there is a small mistake here. T1, D1, this should be D1, T1, D2, this should be D2, D3. So here D3 and D2 starts conducting, and here T4 and D3. So this is the current waveform of ID3. So what is the average output voltage? What is the average output voltage? What is the average value of this waveform? 0 to alpha it is 0, pi to pi plus alpha it is 0. So if I take the average, it is given by Vm by pi into 1 plus cos alpha. Alpha is varying from 0 to pi, so average value is always positive, always positive. So if I plot alpha versus V0, this is the variation. Whereas where this is 1 per unit is 2 Vm by pi, 2 Vm by pi. When alpha is equal to pi by 2, this becomes 0. So average value of the output voltage is 0.5. Per unit value is 0.5. Load current is always unidirectional. Load current is always unidirectional. Current is always flowing from positive DC bus to the negative DC bus. I mean, current is always flowing from positive DC bus to negative DC bus, unidirectional. Average value of the output voltage is also always positive. So power input to this bridge is always positive. In other words, source is always supplying power to this bridge. Okay. So if I plot Vi characteristics of this, V0 is positive, I0 is also positive. It is operation is in the first quadrant. Operation is in the first quadrant. What is the displacement angle? What is the angle between the input sinusoid and the fundamental component of the source current? Fundamental component of this source current. Again, it is an odd function. Odd harmonics are present. The angle between the fundamental component of the input voltage and the fundamental component of the source current is found to be half of alpha. In other words, it is alpha by 2. Okay. Alpha by 2. So displacement factor is cos of this angle. Minus sign indicates that power factor is lagging. Even the displacement factor is lagging. So because if you see here, sinusoid, input sinusoid, fundamental components cuts the zero axis at somewhere in here. So if you see that fundamental component lags the fundamental component of the voltage, hence the power displacement angle is lagging. What is the RMS value of the fundamental component of source I? Procedure is the same. It is found to be this value. You need to find the RMS value of the source current. This is the value, and the power factor is given by this equation. The procedure used is the same as that we used in the full bridge uncontrolled rectifiers. Okay. So what is our observation? If alpha is equal to 0, if alpha is not equal to 0, the duration for which the thyristor conduct is not the same as that of the diode. Gamma for thyristors is not equal to gamma for the diodes. So therefore average current rating of thyristors is less than average current of the diode. Let's see, we will take a second configuration. In the previous configuration we connected T3 and T1 in one leg. Now we are connecting T3 and T1 in two different legs. We have T1 and T3 making a common cathode configuration and D4 and D2 making a common anode configuration. At omega t is equal to alpha, T1 is triggered. The operation of the circuit is same as that of the previous one. Source T1, load D2. What happens at omega t is equal to pi? In the lower arm, D4 and D2 form a common anode configuration. Potential of B is higher than potential of A from omega t is equal to pi plus. So immediately D4 starts conducting. In the upper half, T3 is forward biased, but then we have not applied a gate signal to T3. So therefore T3 is not started conducting as yet. So, since the load is inductive, current starts flowing between T1 load and D4. So, current starts flowing through T1 load and D4. In the previous case, current started flowing from D2 D3, so D2 D3. So, current freewheels through T1 and D4. Voltage applied to the load is 0, source current is also 0. At omega t is equal to pi plus, T3 is triggered. The moment T3 is triggered, cathode potential is same as the potential of B, which is higher than the potential of A. A negative voltage appears across T1, T1 turns off. T1 turns off. So, again line commutation, the process is known as line commutation. I am using the input voltage to turn off T1. So, from omega t is equal to pi plus alpha, T3 starts conducting, T3 D4 was started conducting at omega t is equal to pi plus. So, this is the equivalent circuit. This is the equivalent circuit at omega t is equal to pi to pi plus alpha. And this is the equivalent circuit at from 2 pi to 2 pi plus alpha. So, here are the various waveforms. Trigger G1, gate signal to T1, gate signal to T4, T1, D2 they will conduct from alpha to pi, at from pi to pi plus alpha, T1, D4 same like one thyristor and one diode conducting from pi plus alpha to 2 pi, T2 D4 starts conducting, and from 2 pi to 2 pi plus alpha, T3 D2 starts conducting. T3 D2 starts conducting. So, if I plot the current flowing through thyristor T1 with alpha, we will find that T1 is conducting from alpha to pi plus alpha, and D4 if I plot any diode for that matter, pi to 2 pi. So, you will find that gamma for T1 is pi radians and gamma for diodes is again pi radians. So, average current rating of thyristor is same as that of the diodes. The source current waveform is the same as the previous one. Alpha to pi it is positive I naught, pi plus alpha to 2 pi is minus I naught. Average value of the output voltage is again Vm by pi into 1 plus cos alpha. Waveform is the same, only the devices they are conducting are different. Devices that are conducting are different. Please, this should be T3, 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 T3.